Okay, this is Dmitry Mendeleev here. We've talked about him. He is the father of the periodic table. He's the guy that created this thing. And his whole goal here was to take this whole jumbled mess of all these different ingredients of the universe, these things that are called elements, and try to make some sort of sense out of them and try to organize them. And he was really into playing cards, and he kind of thought of this as like sort of a jumbled mess of cards. And he knew that you could take cards and organize them, and he wanted to do the same thing. He wanted to kind of put them into organizations like the suits of a deck of cards or the numbers of a deck of cards. So notice we can organize it this way, right? And they change by suit, or we can organize it this way and they change by number, right? And he had this same idea. And what we need to talk about this week is the idea that the periodic table is organized in the same way. They are organized in this way, and they are organized in this way, along with being organized by their number of protons, which is the atomic number. Don't forget that red slides are where you have to take notes. You should have your notes handout ready to go. Don't forget to look for the owl and let me know where he is. And remember to fill in all of this stuff that you see here. So if you work for a company that designs and builds airplanes, it would be really helpful if you had the ability to know what type of materials would work well for what you want to do. So for the body of the airplane, you would want something that's really strong so it doesn't fall apart, but it's also got to be very lightweight. And I would think that some of the engine parts, like some of the rocket engine parts and things like that, would have to be able to withstand a lot of heat and not melt very easily. So they would have to have a very high melting point. So it would be nice if we could know what type of materials to use in order to make those things. Well, that's really the key to the organization of the periodic table, because the periodic table puts elements into rows and columns with similar characteristics or similar properties. This is basically organizing all of these elements that make up the universe in a way that puts them together by how they behave in the universe. Are they a gas at room temperature? Do they conduct electricity and heat? Are they shiny? Can you bend them into shapes? All of these different things that we would describe as physical properties or chemical properties of things. Like, do they react with things? Do they catch on fire easily? Things like that. We have the periodic table organized in a way that puts those things together by their properties. So we're going to talk a lot about that today. You can see here this idea. We have nonmetals and we have different types of metals, right? And we have halogens and all sorts of different things here. So we're going to talk about how this is organized and start to get to know the characteristics of these groups a little bit. So think of them as like different actors in a play or something like that all have different type of personalities to them. Okay, so first of all, a horizontal row, something that goes this way, that is called a period in the periodic table. And by the way, periodic just means something that happens over and over again. Think waves, right? We actually talk about the period of waves. So something that happens in a regular amount of time that kind of repeats over and over again. That's what we mean by something being periodic. So each of these rows has the same number of electron shells. And we've talked about the Bohr model and electron shells, so you should understand what that means. And each of the vertical columns, the ones that go this way, have the same number of valence electrons. You should also know what that means. That's extremely important when it comes to the idea of how they react with things. So, is this one a period or a group? See if you were paying attention there. Yeah, that's a group. That's a period. All right. So, let's talk about the periods first. There's going to be a relatively small amount of stuff to say about this, and really what we want to concentrate on is the groups, but there is a little bit to talk about the periods. Okay, all the elements in the period have the same number of electron shells. Let's take a look at this and see if we can figure this out. So, let's look at the first row here, right? The first period. Well, hydrogen has one electron total, so it's only got one valence electron, right? Okay, that makes sense. Now, if we go to the second row here, we start off with lithium, and lithium has, well, remember, hydrogen has one electron, one proton and one electron. Helium has two protons and two electrons. Don't worry about this box right here. That's just kind of showing that hydrogen can fit either over here or over here, but don't worry about that. So helium has two protons and two electrons, and lithium has three protons and 1, 2, 3 electrons. So how many can fit in the first shell? Well, 2. So the third one has to go into a second shell. Now, what if we continue on with this? If we look at beryllium, right? Beryllium has 4 protons and 4 electrons. So we would have 1, 2, 3, and we would just have to draw one more here to make this into beryllium, right? And if we go over here, boron, well, that has 5 protons and 5 electrons, right? So we would have to draw one more. And then we get to carbon, which has 6 protons and 6 electrons. And then we get to nitrogen, right, which has 7 protons and 7 electrons, right? So we'd have to draw one more in there. And then we get to oxygen, which has 8 protons and 8 electrons. We have to draw one more in there. And then we get to fluorine, that has another electron that we have to draw in there. And finally, we get to neon, which has one more electron. Now look what happens at this point. How many electrons do we have in this outer shell? Well, let's count them. 1, 2, 3, 4, 5, 6, 7, and the magic number 8 electrons in its valence shell. That's all it can hold, right? And then we go on to the next column, right? And then this guy has, let's see, 1, 2, 3 electron shells. And then we could do the same thing for that one, but then the next one is going to go to 4 electron shells and 5 electron shells, and that will bring us to one of my favorite elements, which is francium. Take a look at this little clip.
I'm changing my tie to alkali metal tie.
You have an alkali metal tie?
It's a new tie I've just got. This one's a Dutch one. I was given it on Saturday. He gave me this one. So here you can see we have the alkali metals.
Oh, hang on, where are they? Yep.
Here. And the alkali metals are very reactive. So we've seen that lithium doesn't react very much. But then as you go to sodium, and then to potassium and rubidium, the violence of the reaction gets more and more and more. And cesium is even greater. I don't know whether the people making this tie were so frightened that they didn't put it on, but in each of these cases the reaction is removing one electron after another, one electron from the outer atom, outer shell of the atom, and the bigger the atom, the easier it is to remove the electron. And as you go down the periodic table, the size of the atom increases, so it's easier to remove the electron. So francium would almost certainly be even bigger than cesium because it's a whole row lower down, and so that should react with water with enormous violence. But unfortunately, francium is very radioactive, and you can't get a nice lump of francium the sort of size that you'd like to throw in water to make the YouTube video of the century. Francium, which is named after France, was discovered by one of Madame Curie's pupils in 1939, 5 years after Madame Curie herself died. I always thought that it was Madame Curie that discovered it, but in fact it was discovered after her death. But its properties would probably be similar to those of cesium if it was not very radioactive. But radioactivity like that makes it very difficult for chemists to study the chemistry in enormous detail. Chemical reactions are really quite sensitive to temperature, and radioactive materials, as they decay, give out energy. So the compounds themselves tend to heat up. A lump of plutonium, which is very radioactive, is really quite warm to touch. And francium, which I think is more radioactive, is probably very warm. So I think the melting point of francium will be lower than that of cesium, because the melting points go down the group. And because it will be generating heat, almost certainly francium would be a liquid at room temperature. But I've never seen it. It might well be coloured as well, because cesium is golden coloured, so I would not be surprised if francium was red, but I have no idea, and I'm not sure if anybody knows.
So there we have francium at the end, and as he was saying, these guys get more and more reactive as we kind of go down here because their electrons are kind of further and further out. That should make sense, that each one has one more shell than it is away from the nucleus. And remember, positive and negative attract each other, so the farther away those electrons get from the nucleus, the easier it is to take them away because they're not so close. Think of like two magnets that you're pulling apart from each other. As you pull them away from each other, that attraction between the two magnets gets weaker and weaker. So the attraction between the positive protons in the nucleus and the negative valence electron way on the outside of that atom gets weaker and weaker as it moves farther and farther away because it has more and more shells in that atom. So it's easier to pluck that atom off and cause a chemical reaction, and that creates, well, a bunch of this kind of stuff. Well, sort of. This is actually not a francium bomb. There is, as far as I know, there are no videos or pictures of francium explosions that I can find on the internet. There's a lot of fake ones out there that if you do your research, you'll see that they're just nuclear bomb tests and things like that. But that's about what a francium bomb would look like if you had a little chunk of it. I guess fortunately there's only a few grams of francium on the entire Earth, and the reason for that is because it has what's called a half-life of 22 seconds, which means if you have a sample of francium, it's radioactive and it actually decays, which means its nucleus breaks apart and it turns into other elements. And so if you have a sample of francium, half of that sample will turn into something else in 22 seconds. And then 22 seconds later, half of what you had left will turn into something else. So you can imagine it wouldn't take long until you have pretty much nothing left. So those are the periods. Remember, 1 shell, 2 shells, 3 shells, 4 shells, 5 shells, and 6 shells is how the periods are organized. All of the elements in this row have 1 electron shell. All of the elements in this row have 2 electron shells. All of the elements in this row have 3, 4, 5, and 6. And that really affects their reactivity because it makes it easier to pluck off this little guy that's way out here outside on the outside of the atom. All right, as I said, we need to talk a little bit more about the groups. Okay, so let's take a look at how this works. So hydrogen has 1 valence electron, and it is in the alkali metal family. All right, so here's hydrogen right here, and this little dot represents how many valence electrons it has. Not how many electrons total, just the valence electrons, just the ones that are on the outermost shell. So what do you see as a pattern here? I see 1 valence electron, 1 valence electron, 1 valence electron, something, 1 valence electron, 1 valence electron. Now let's look at this. Here's the second column, right? What do you notice? 2 valence electrons, 2 valence electrons, 2 valence electrons, same thing for this whole column. Then we kind of skip all the transition metals in the middle because, well, they're confusing. Okay, so don't worry about it. So let's skip over to this side of the periodic table. What do we notice? 3 valence electrons, 4, 5, 6, 7, right? Almost to that full 8 outer shells that we have here, right? What about helium? Helium's kind of weird, right? It's got 2. Well, why is that okay? Because for helium, helium is kind of an exception here because he only needs 2 to have a complete outer shell. So that's a little bit of an exception to this rule, but it makes sense, right? Because all of these guys have full outer shells. It just happens that helium is the only one that's allowed to have a full outer shell with only 2 valence electrons because it only has 1 shell. Okay, so hydrogen all have 1 valence electron in that column. Over here, we can look at fluorine and that entire column. 7 valence electrons in the halogen family. That's kind of an important thing. All right, so we can look at it at a sort of big picture kind of level and say that about 75% of the elements are metals. All of these guys are metals. Most of the ingredients of the universe are what we would call metals. So what exactly do we mean by a metal? Well, I think you know it when you see it. So think about, how do you know that something is metal? Well, they're usually solid at room temperature, with the notable exception of mercury. They are usually reactive to chemicals. Think about it. Metals, a lot of times, what happens to metals if you leave them out in the rain? They rust, right? Well, that's a chemical reaction. One exception to that that's very interesting is gold, and I think that's probably the main reason why we use it as a basically as a source of money. Now, yes, gold is pretty and people like how it looks and things like that, but actually the reason why we use it as our kind of foundation of money, even today, the American dollar is tied to the value of gold. So the reason why that is because, well, think about like if you were an Egyptian pharaoh or something like that, right? And you had this big amount of wealth that you had put together, and you wanted to store it somewhere. Well, if you have that wealth in gold and you store it somewhere, that gold, nothing's going to happen to it. It's not going to rust. It's not going to decay. It's not going to break down. Nothing's going to happen because it doesn't react with the outside environment. So that gold is going to continue to be there for your children and your grandchildren and your great grandchildren. Thousands of years later, that gold will stick around, just like these gold coins you see that are many, many, many years old. Some of these are thousands of years old. All right. So metals are shiny, usually, right? They have a high luster. They are malleable, which means you can bend them into shapes, which is why we use them for things like this and things like jewelry and stuff like that, because you can bend them into different shapes. They are ductile, which means you can stretch them into long, thin wires. I want you to look at this little video clip so you get a sense of what do we mean by malleable and ductile.
Iron is malleable at high temperatures. Therefore, it must be heated up before forging. When it is red hot, it can be pounded with a hammer into a desired shape. Likewise, 2 pieces of red-hot iron can be linked together to form part of an ornamental trellis, for example. Copper and aluminium are malleable at room temperature. Metals can be drawn into rods and wires by heating and pulling apart. Copper can be drawn into the very thin wires used in electric cables.
Okay, so they are also good conductors of heat and electricity. You know that. So here are a bunch of different metals from the periodic table. The metals also include these guys on the bottom here. These are the actinide metals that you see highlighted down at the bottom, and the lanthanide metals that you see highlighted down there. These guys have a lot of interesting properties. A lot of them are magnetic. A lot of them are radioactive. So we have the alkali metals. We have the alkaline earth metals. We have the transition metals. So let's talk about the first row, the alkali metals. This is the first group. they all have one valence electron, as we talked about. That's pretty important because that makes them very, very reactive. I want you to think about this like all this guy has to do is get rid of this one electron, and then we kind of default to the lower energy level here. So if he just gets rid of that one electron, then we have 2, 4, 6, 8 valence electrons, the magic number, what every atom is looking for. So take a look at this, okay? So alkali metals have one valence electron. So which one is the alkali metal here? Well, look at the ones on the outside, right? So this has one valence electron. So that is the alkali metal. That is sodium. Halogens, on the other hand, a group that we'll talk about in a moment, have 7 valence electrons. That's the guy on the right here, chlorine. And so these guys are kind of a match made in heaven. We'll talk about this quite a bit more in upcoming weeks. But basically, this guy wants to go over here and fill in this little empty space here. And then both atoms will have full outer shells and be very happy atoms and will kind of stick together. And when they do, that makes salt. All right, second group, alkaline earth metals, 2 valence electrons. So these guys are somewhat reactive, but because it's a little bit more difficult for them to give up the 2 electrons, they're not quite as reactive as the other guys. So what alkaline earth metal is this? You should be able to figure this out. I'll give you a second to think about it. What should you be looking for here if you're confused? How about that, right? The atomic number. That tells you which element it is. And what is number 12 on the periodic table? It is magnesium. That's what magnesium looks like, and you actually are probably familiar with magnesium because on the 4th of July, you have probably played with sparklers, and you may have noticed that there's almost like a metallic looking dust on the end of it where you burn it. Well, that's magnesium. And actually, a lot of these type of metals, a lot of the alkaline earth metals and several other types of transition metals and things like that are used in fireworks and stuff like that. Each different one kind of burns a different color, so that's how they get the reds and the blues and the yellows and all the different colors that you get with fireworks. Some of them make a really loud noise when you burn them, and that's how you get those explosion sounds. And so people that do fireworks are actually metal chemists, basically. They really know a lot about the chemistry of the different metals, so that's a really useful thing. And again, remember, the periodic table is organized in a way that they should be able to look at that periodic table, and based on where those different elements are on the periodic table, they should be able to kind of know what they will do when they light them on fire and use them for fireworks. So that would be useful to somebody that does fireworks. All right, so transition metals. These are a big group in the middle of the periodic table, and this includes most elements that we think of as metals. Think of iron, copper, aluminum, gold, silver, titanium, stuff like that. That's what we're talking about there. All right, next up we have the rare earth elements. These are made up of the 2 series of elements, the lanthanides and the actinides, and these are the guys down here, the ones that have been kind of taken out of the periodic table and stuck down on the bottom just to make the periodic table a little bit more convenient. So lanthanides are there and actinides are there. One of these, as I said, these guys tend to have some interesting properties. A lot of them are radioactive, and a lot of them are very magnetic, including this one that's highlighted down here. That's called neodymium, and we've probably used some neodymium magnets in class, and they're really, really powerful magnets. All right, so that gets us through the metals. Now let's talk about the metalloids or semi-metals. These have properties of metals and properties of nonmetals. Remember, everything from here over to the left is metals. Everything from here over to the right is nonmetals, and they have kind of opposite properties of each other. So these guys that are in between, again, things on the periodic table are organized by how they behave in the world, and so these guys behave in a way that is kind of in between metals and nonmetals, so we put them in between metals and nonmetals on the periodic table. Makes sense. All right, these include semiconductors. Semiconductors are called semiconductors because they kind of conduct electricity, and that's really important because that fact, and especially in the element silicon, which is a semiconductor or a metalloid, that fact that they can kind of conduct electricity, or they can conduct electricity when we want them to conduct electricity, or not conduct electricity if we don't want them to, that fact alone is the reason why we have anything that you would consider a digital piece of equipment. Computers, phones, TVs that are digital, any of that kind of stuff is all because of silicon mainly. That is why we have that stuff. So that's a pretty important element in our lives. All right, so these guys tend to be brittle, which means if you smash them, they break, they don't bend. They can have luster sometimes. Okay, nonmetals. Nonmetals are, well, they're not metals. So they have properties that are not the properties of metals. Makes sense, right? So they don't conduct electricity. They're poor conductors. They are brittle. They are not malleable. They are dull, so they do not have high luster like metals. They can be transparent or translucent sometimes. Is that rectangle there transparent or translucent? No, that would be, what's the word? Oh yeah, opaque. That is transparent. And so that, all of that stuff there is probably made of a non-metal substance. All right, let's talk about a specific group in the nonmetals here. These are the halogens. This is group number 17. This is right here on the periodic table, the halogens. And these guys are called the salt formers, kind of like transformers. These are the salt formers. Well, why are they called salt formers? Because they like to form salts. So the halogens exist, generally speaking, at room temperature in all three states of matter. They can be solid, liquids, or gases. And all halogens have 7 electrons in their outer shells, which makes them very, very, very reactive. The noble gases, on the other hand, are basically the opposite. Okay, so these guys, what does this mean? They have the inert gases have full outer shells with 8 electrons. What does that mean? Think about the octet rule. Yeah, that means that they are full, that they are happy, satisfied atoms. And what does that mean? Well, it means they don't react with anything. They don't like to get together with other atoms, right? Hydrogen and oxygen like to get together to form water. Sodium and chlorine like to get together to form salt. The noble gases don't really like to do that. They don't like to get together and bond with other elements to make compounds. So they kind of stay by themselves. And that's why they call them noble gases. Think of like kings and queens. They like to kind of shut themselves off, and they don't really mess around with the regular people, right? All right. So they don't want to gain or lose any electrons, so they are happy the way they are. So they are quite happy not reacting with other elements because they have full outer shells. Take a look at these 2 examples here, right? Full outer shells, 8 electrons in their outermost shell. Who's in this family? Well, the things that make these type of signs are in this family. We have helium, neon, argon, krypton, xenon, and radon in this family. And so whenever you talk about a neon sign, neon is this specific color right here, okay? Gives off that color light when you put electricity through it. If it is this color, then it's not a neon sign, it's an argon sign. We tend to call them all neon signs no matter what color they are, but really this would be an argon sign. If it was this color, it would be a krypton sign. Yes, krypton is a real thing, not just in Superman. Although in Superman it's kryptonite and the planet is called Krypton, but yeah, I'll stop being a nerd right now. Anyway, xenon is that color and helium is that color when you put lights, when you put electricity through it. Okay, so periodic table. Periods go this way, right? These are periods. And the periods are organized in a way that they have an increasing number of electron shells as we go down in the period. So this one has 1 shell. This period has 2 shells. Please excuse my horrible drawings. This period has 3 shells, 2, 3, and so on, right? The vertical columns are called groups, and the groups are organized in a way that all of the elements in each group, again, skipping over all these transition metals here just because they're weird. They don't like to follow rules. So we're just going to kind of leave them alone. You'll learn more about that when you take chemistry in high school. But for now, we're just going to leave them alone because they're complicated. So, but as long as we skip that, they basically follow these rules where they have an increasing number of valence electrons. Super, super important for talking about chemistry. So these guys have 1 valence electron. This entire column has 2 valence electrons, 3 valence electrons, 4 valence electrons, and so on. And you guys should know something a little bit about each one, okay? These guys are very reactive. These guys are somewhat reactive. These guys are the ones we're talking about usually when we talk about different types of metals. These are your metalloids, which are kind of in between, and then we have these guys here, which are also very reactive, and because they have 7 valence electrons, they're going to tend to want to react with these guys over here who have 1 valence electron. And last but not least, you have the noble gases, which have a full outer shell and don't like to react to anybody. And I'm just going to scribble over this a little bit more just to make it look even better. We'll talk about this a lot more in class, and I will see you then.